All right, welcome back to the part 2 of the Introduction to Hydrocarbons, the Chapter 4 material. We just finished off talking in the last video about representations of organic molecules, line drawings, wedge and dash, and formula drawings. Now I want to go forward and look at a little bit more about the structure of those hydrocarbons. I want to introduce the concept called constitutional isomers. Now, what constitutional isomers are molecules that have the same molecular formula, same chemical formula, but a different connectivity of atoms. And so I'll move myself out of the road and show you an example of what we mean by that. So same chemical formula, different connectivity of atoms is the definition of what constitutional isomers are. And of course, we've already seen an example of this, where octane and isooctane in gasoline have the same chemical formula, but as you can see from their line drawings there, the connectivity of those atoms now is somewhat different. And so this is an important concept, and there's a useful process to kind of thinking about how different constitutional isomers of molecules might arise. And of course, the more carbon atoms that are present in a hydrocarbon, the higher the number of constitutional isomers can be for the various alkanes. So for example, for propane C3H8, there's only one isomer available. For butane, there's 2. For pentane, there's 3. And it goes up quite rapidly until you get up to 20 carbon atoms. There's 366,000 possible different structural isomers of those molecules. And up to C40, that's a number that's quite, I would say, quite large and hard to a little bit comprehend. And so I just want to show you for a minute what we mean by this and what the different constitutional isomers might be of these molecules. So I'll focus just on a very quick and simple example, C5H12, the different constitutional isomers that might be present in that molecular formula. So I'll just switch to being able to draw on the iPad here. So C5H12 is that formula. I see I'm a little bit in the road here. I'll just kind of get to the side. C5H12 is that molecular formula. And so you can draw this out, and I'll do this in line drawings. And if you're still kind of practicing that skill, you can draw these molecules out in formula or even wedge and dash drawings just to see if you can follow along with what we're drawing. So one of the constitutional isomers that I could draw for this particular hydrocarbon is that one there. That's just the line drawing. Again, each of those corners depicts an sp3 hybridized carbon atoms, and the two ends depict an sp3 hybridized carbon, each with 3 hydrogens on the end. The 3 corners have 2 hydrogen atoms on them. So that's one of the constitutional isomers that we can draw. Now, I can imagine another connectivity for this particular molecule. We're now again just using the line drawing. What I'm showing is that at this point here, and I'll just connect that line just to make sure that there's no gap there. At that point there's a carbon attached to another carbon there, then a CH2 and a CH3 over here. So only a single hydrogen atom at that center, but that's got exactly the same chemical formula, C5H12 if you count them up correctly. C5H12, same chemical formula as what we started with, and but a different connectivity in those atoms. And then there's another isomer that I can draw, another constitutional isomer that I can draw for this molecule. Again, in the line drawing. So the line drawing depicted there, and what we're looking at here is a single carbon atom at the center here, surrounded by 4 CH3 groups all the way around that center. And so if you draw that out or make the model of it or think about what that would look like in a formula drawing, you get the idea of what this constitutional isomer might look like. But again, the chemical formula is identical, C5H12 for that particular molecule, just like the other two that we could draw here. I'll make these lines a bit better here as well too. That's not a great drawing now that I've messed it up a bit. Oh, Do that in black just so I don't confuse myself here. So that constitutional isomer, and the one we started with, this straight line constitutional isomer. So we've got this isomer, we've got this one, we've got this one here. And now, maybe if you're playing along a little bit and kind of drawing constitutional isomers of C5H12, you might be thinking to yourself, hang on a minute, I've been able to draw another constitutional isomer that looks different than the one you drew. You say, I was playing around and I came up with a molecule that looks like this. You say, well, that looks different than anything that we've drawn on the other three panels. It's different than anything we've drawn on the other three panels. It does have the same chemical formula, C5H12, but I'll try and make the case that that molecule is absolutely 100% identical to the one that we drew in the second panel. The one on the second panel that we drew is that isomer there, and all we're doing is just showing this molecule in a different depiction here. So this is just a different depiction of this molecule here, where we're just drawing it the other way around. And so this is a bit of part of the skill of learning to look at and draw organic molecules, is to try and recognize when you've drawn two molecules that are identical with respect to each other as well. Okay. If you've got any questions on that, we'll take them on Fridays. If we've got any questions on that, we'll take them on Friday's question and answer session when we activate that in class there as well. Okay, so the next thing we'll take a look at, now that we've talked a little bit about constitutional isomers and their structures, is we'll take a look at the chemical and physical properties of them. So the constitutional isomers that have different connectivity of atoms, as you might expect, they'll have different physical and chemical properties between the constitutional isomers. And so one of the chemical or physical properties that we might imagine taking a look at, one of the physical properties in particular, would be things like boiling points and melting points. And here we're showing on the screen the fact that octane and isooctane have somewhat different melting points and boiling points. So for example, the straight chain octane has a boiling point higher than isooctane of 125 degrees Celsius, and the straight chain, or N-octane as we call it, sometimes the normal octane, has a melting point of minus 57 degrees Celsius. Whereas isooctane's got a bit of a lower boiling point, 98 degrees Celsius, and the melting point is lower as well too, minus 107 degrees Celsius. So you might see a little bit why we use isooctane for gasoline. It doesn't freeze at temperatures like minus 57, which you can imagine being sometimes achievable, or feels like it's achievable, in Manitoba in the middle of winter as well. Of course, the intermolecular forces in these molecules, and we kind of are expecting or hoping to remember a lot about intermolecular forces from general chemistry. It's all van der Waals forces, or those very weak intermolecular forces. London dispersion forces, you may hear a call from time to time, or instantaneous dipole. But those intermolecular forces are different between the two molecules. We might imagine those straight N-octanes just stacking up on top of each other in a way that the isooctane can't, having an influence on the melting and boiling points. Another chemical property that we like to use a lot for looking at the difference between constitutional isomers is the heat of combustion. And so the heat of combustion is as advertised, and you likely have seen this before in general chemistry, or maybe other chemistry courses that you've taken, other science courses, where we take a hydrocarbon, or molecule, any molecule, but in this particular instance a hydrocarbon, so C8H18. We burn it in excess, so it just means that the hydrocarbon is the limiting factor, not the oxygen, so an excess amount of oxygen. That gives us molecules of carbon dioxide and water. And we won't go through balancing these equations, we'll just put it here. And of course you can measure the amount of energy that's given off by this reaction. And so you can measure the heat, the enthalpy of the combustion, the heat of combustion directly, so delta H naught C, the heat of combustion. And for N-octane, we won't go into how you would measure that, but the number you would get there is minus 5,470 kilojoules per mole for N-octane. If you do the same experiment for the isooctane, again, identical molecular formula, the same experiment, excess oxygen, 8 molecules of carbon dioxide, 9 molecules of water, what you observe is you get a little bit less energy out of the isooctane than you do from the octane. You're taking that molecule and you're taking and burning it down to the lower energy carbon dioxide and water, but you get out less energy, 5,460 kilojoules per mole. That means there's a difference of 10 kilojoules per mole between these two molecules that have identical molecular formulas, identical chemical formulas. So the observation that we're seeing here, what we're seeing here is that there's less energy released by burning 1 mole of isooctane than there is by burning 1 mole of N-octane, which I think is really interesting. The same chemical formula, there's a difference in the molecules. And do we see this trend continued across other molecules? And so this is a figure right out of our textbook, figure 4.1, that we've reproduced here. You see that same trend with other isomers. And so you kind of look, and so what we like to do with these kinds of observations is to see, can we observe trends in the observations we're making? We're making measurements in an experiment here. We're taking different hydrocarbons with identical chemical formulas and burning them. And what we're observing is differences in the energy that's being released. And so this figure does kind of try and depict it quite nicely, where that the N-octane or the straight chain octane's got more energy than the branched hydrocarbons. We've got more what we call substituents on the other hydrocarbons as we go along. There's less energy contained in those. They release energy all going down to the same place. So it's the difference between jumping off a chair to the floor and jumping off a table to the floor. You've got more energy standing on the table than you do standing on the chair, even though you wind up at the same place. And that's the observations we're making with these experiments here. So what we're observing then is that the more branches or substituents that a constitutional isomer has, the less energy it contains. So that's an observation. Well, how do we make some kind of like usable conclusion from that observation? Well, energy we can relate to the general stability of a molecule. You're more stable standing on a chair than you are balancing up high on a table, or maybe even more stable standing on a stool instead of that chair. So this is a way we kind of like to think about molecules. Molecules that contain less energy are more stable in some way. And so our conclusion based on these particular observations is that the more branches that an alkane has makes it more stable. Well, what's the explanation for this? Well, we will come back to that a little bit later. I don't want to start that here. We'll link this up a little bit later when we talk about other functional groups and other stability of things like carbocations. But the reason, and I know you might be thinking about it to yourself at this point, hey, who cares about this little piece of chemical trivia? You're making a big deal out of what seems like not much of anything. It turns out it's kind of a big deal. This observation, and even just knowing this conclusion that branched alkanes are more stable, will help us explain a lot of organic reactions, not just in this course, but in any other organic course you take past this point. And in fact, at the end of our time together, the end of November, first week of December, we're going to use this observation, this conclusion that we just made here, to predict the outcome of a lot of the reactions we're going to talk about in Chapter 7, in particular elimination and substitution reactions. Those outcomes can be predicted just by remembering this little piece of chemical trivia. So it is kind of a useful thing for us to remember and make use of. So that's it for now for this video. And for the constitutional isomers and the stability of alkanes, the next video that'll be posted, Dr. Davis will be talking to you about the conformational analysis of hydrocarbons and looking at the conformation of ethane.